There we go. You go away. There we are. So we're looking at, and 14 we're going to leave for right now. I want to look at 15. Okay, because 15 is one of those ones where, 15 is one of those ones where it's better, rather than trying to get in factor all the way to your goal, it's better to simplify your goal a little bit and kind of meet in the middle. As long as you get them looking the same, you're fine, okay? So, we go through our process as usual, where we let n equal 1, and first of all, 1 to the 4th power is 1. Then we plug in a 1 everywhere we see an n, and we get 1 times 2 times 3 times 5, which equals 30 over 30, which also is 1, okay? Now one question was, does it always have to come out to 1? The answer is no, you just have to get the same thing for both sides. You just have to get things that are equal, alright? So it could be 5 and 5 or something. As long as they're equal, you prove that it works for 1. Okay? So the next thing, we make this statement. And really, this second step should be the easiest step of everything. Okay? Because all you're doing is taking what you have written here and replacing all of the n's with k's. Alright? So you can ignore this for a moment, but we're just replacing all the n's with k's for that second step. Alright? The third step is, as you guys know, where the majority of the work comes in. Okay? First of all, we need to use this to come up with our goal. So everywhere we see an n, we're going to plug in a k plus 1. Because for step 3, we're doing k plus 1s. Alright? So let's look at this goal. Alright, instead of a k, it's now k plus 1. Instead of a k plus 1, it's now a k plus 1 plus 1. So k plus 2. Here we have a 2k plus 1, which you can see here in green. I have to now multiply 2 by a k plus 1, and then add another 1. So we get 2k plus 3, there in green. And then finally, this part here, that was a 2n squared plus, or I'm sorry, 3n squared plus 3n minus 1, we're now plugging in a k plus 1. So that you have to be a little more careful with, because you have to remember to FOIL. Okay? You have to FOIL the k plus 1 squared, then distribute the 3, and then simplify. But this would simplify down to 3k squared plus 9k plus 5. Alright? And you'll see why the yellow brackets are there in a moment, but that's it. Yes?
Where'd you get 2k plus 3 from? Would it be 2k plus 2?
Well, you distribute 2k plus 2, but then you have this other plus 1.
Oh, okay.
So you gotta add another one.
Okay.
Anything else? Questions up to this point? Okay, so now we need to handle the left side of the of what we're trying to prove. So we're taking the sum from I equals 1 to k plus 1 of I to the 4th. So that's 1 to the 4th plus 2 to the 4th all the way up to k to the 4th, and then k plus 1 to the 4th power. And all of this, from 1 up to k, is what we just had in step 2.
Wait, can you explain that again?
We expand out the sum,
Yeah.
all the way up to k plus 1 to the 4th. Everything up to k is what we just had in step 2.
Yeah.
Alright? So, we're going to substitute in what we had in step 2 for all of this, and then we just have this k plus 1 to the 4th. Which you can see I'm going to get a common denominator so I can put stuff together. Yes?
I'm sorry, so your goal, how does that relate to the third step? Like if you're plugging in k plus 1 for every k, then where does the n equals k, like how does that factor into it?
The n equals k part of it?
Yeah.
That factors in right here because we're replacing, the reason why we stated this is so that we could take, this and put it in for all of this. Okay?
Okay.
And then that extra term is right there.
And you're trying to get n equals k plus 1 from that.
We're trying to get, well, this is the relationship 1 n equals k plus 1. And then from all of this, we're trying to get our goal. We need to prove that those two expressions are equal.
Okay.
Okay? Yes, Jason?
Is this the same thing like you plug in the formula, like the first term plus the second, like the last term and divide by 2 times the number of terms? Like you're
That
supposed-
only works for an arithmetic sequence. Okay? That's a formula we learned for arithmetic, but that doesn't work every time you have a sum. Okay? In fact, a lot of what we're proving is other formulas like the one we have for arithmetic. Okay? In fact, guys, that arithmetic sequence, the partial sum formula, that's something that we would prove using this process. Okay?
For the goal, where it says 3k squared plus 9k,
Mm-hmm.
don't you want to plug in k plus 1 for the k there?
We did. See this?
Oh,
We plugged it in here, and then we FOILed that and distributed the threes and combined all our like
I
terms.
didn't think that looked right, but I guess it is.
Yeah.
The
That's
second,
right.
the second term, in the final circled
Mm-hmm.
area, where do you get the 30 in the numerator from?
Okay, here, once I get to this point, now I'm going to get a common denominator, so I multiply by
Oh,
30 over
okay.
30. That's kind of moving to our next step. Okay? So moving to our next step, I multiply by 30 over 30 so I can add these, and one thing that will be helpful for you is to notice there's a k plus 1 here, and there's a k plus 1 over here. I'm going to factor those out. Okay? If I take out the k plus 1, this entire thing is going to be over 30 because I have a common denominator now. But, oh, go away. If I take out the k plus 1, I've got the k, the 2k plus 1, and the 3k squared plus 3k minus 1 left over. Okay? And then if I take out a k plus 1 from this 30 times k plus 1 to the fourth,
Be 30 times k plus 1 to the third.
yeah, I have 30 times k plus 1 to the third left over. That's in the brackets. Okay?
Wait, I was really
You just factor out k plus
So I factored out,
Oh, I did that.
this and one of these four. Okay? And that's right here. I pulled it out. Now, this is why I have those yellow brackets in there. Because this is one of those cases where to continue going with this and try to make it look exactly like our goal is going to be a ton of work. You're going to have to do like polynomial long division twice after multiplying all this out. Okay? Now, we still do have a lot of work, but that's even more work than we absolutely have to do. The simplest way is to recognize, notice in our goal, there's a k plus 1, and there's a 30 in the denominator. I already have those two parts. So really, all I have to show at this point is that what's in the brackets here equals what's in the brackets down there. So I know it's a lot of foiling, a lot of multiplying out, but I would multiply out everything here and combine like terms, and then I would multiply everything up here and combine like terms.
If this is a test question, you would want to do that, or this would never be done?
Yeah, well, I probably wouldn't give you one because I want you to do more than one problem on a test.
Yeah.
So, but that's what you could do here. Let me just real quick. Do this. There we are.
Yeah.
So I'm gonna capture this part.
Yeah, if you're missing one little number.
Yeah, that's also why I wouldn't probably put this on a test because I'm testing to see whether or not you can prove with math induction, not how well you can FOIL. You know, that's just not the point of my
Is it always gonna be able to?
assessment.
Is it always gonna be able to turn into the goal? Or
It
is
should,
So it like. Okay.
if you do everything right, it will. Okay, so let's actually.
So they'll never get you wrong.
I will never give you a wrong one. It's possible you could run into one that's wrong, but okay. So here, the question is, are these equal? These are the two sets of brackets. You'd have to multiply this out. Okay, so this right here, that'd be 2k squared plus 4 and 3 is 7k plus 6 times 3k squared plus 9k plus 5. Alright, if you're not good at multiplying stuff like this, you need to get good fast. Alright, you need to go home and do some practice. Yeah. So, I'll just do this pretty quickly here. This is going to be 6k to the fourth. Our k cubes, we're going to have 18k cubed and 21k cubed. So 18 and 21 is going to give us 39k cubed. Our k squares, we're going to have 10, and 18 is 28, plus another 63 is 101. No, 28, that'll be 91. So you can make a little mistake real easily with this. And then we need our k terms. So that's going to be 35 plus 54, that's 89. K. And then our constant is going to be a plus 30. Alright? So this ought to equal that. Alright? Yes?
What happened, like, on the numerator for that? I feel like I'm looking at the wrong thing.
okay.
Oh no, it's there, never mind.
Okay.
Yours is just smaller, mine's like longer.
Okay. For this, let's say we're going to have 2k squared plus k times this. So I'm going to make it, that's going to be 6k to the fourth plus, that's 6 and 3 is 9, 9k to the third, and then, and then we have a minus 2 and a plus 3, so that's a plus 1k squared. And then for the k's, we're going to just have a minus k. Alright, so it's going to be that plus this multiplied out.
Yeah.
Okay, so that's going to be 30k cubed. I know I'm doing a lot, but it's going to be plus a 90k squared plus a 90k plus 30.
Wait, where did you just get that from?
I multiplied all this in my head. I know you guys know how to do that, so I'm not going to take the time to write it all out. You know how to multiply
Oh,
k
'cause
plus
it's
1
k
times
plus
k plus 1
okay.
times k plus 1. So,
Wait, you wrote 30k cubed? Wait, what, do you have 92 times?
yes, because this k plus 1 cubed is k cubed plus 3k squared plus 3k plus 1. And then you have to distribute the 30 to all that. Okay. So, oh, you're all set?
Yep.
Great. Alright, you can just leave it here. Thank you.
Thanks.
Alright, so now we have 60 k to the fourth plus 39 k cubed plus
Wait. So it should be 6K before.
6, yeah, thank you. 6 k to the fourth plus 39 k cubed plus 91 k squared plus 89 k plus 30, which just happens to be the same thing as that. Okay? So now we know, going back to our problem, that these brackets equal these brackets, therefore we've reached our goal. Okay, we already knew the k plus 1 was there and the 30 was there. We just had to show the brackets were the same. Okay? Yeah, simple as that. Now I don't pretend that this is easy, okay? This is a challenging topic, a really challenging topic, alright? It's gonna stretch your mind, and it's gonna kind of force you to really be careful about some of those fundamentals. I mean, you guys learned how to FOIL in Algebra 1, okay? But that's a process that's really simple to mess up if you're not careful. So just please do be careful with those. All right, now 14, I'm gonna have you guys look at with a friend and compare what you did, all right? And if you both are stuck, then I can intervene and help you out, figure out how to get to the end. All right, but are there any questions on 21 to 24?
Sure.
Did you check Slater?
Just don't expect me to contribute much.
No, I couldn't.
Okay. In the future, I know all the odd answers are in the back of the book, and the evens are on Slater, at least the vast majority. So, does someone have an answer for 22? You do, Olga?
I had 25,333.
25,333.
That's what I got, yeah.
Others got that as well? Okay. And then how about for 24?
16,000.
10? 16,010? No? What did we get?
I got 671580. That's so hard to say.
So 671,580 is what you should get there. Did others get the same thing? Okay. Always like to double check. So.
Are we going to go over 25?
Yeah, we can look at 25 as well. 25 is a hair different because here we were only trying to prove something for n greater than or equal to 4. So guess what? If you try to use the process exactly the way we've been doing it and plug in n equals 1, it's not going to work. Because this doesn't work for n equals 1. It says it only works for n greater than or equal to 4. So notice here on the first step, we're going to say let n equal 4. Alright? How many of you caught that? And did it like that? Alright? A few of you. Good. Good. Alright? So, 4 factorial is 24. 2 to the 4th power is 16. And 24 is greater than 16. So it works for n equals 4. Okay? Now, we're making the statement that for some value n equal to k, k factorial is going to be greater than 2 to the k. Alright? Again, easiest step in the whole process. Just rewrite the problem, but put k's in for n's. Finally, we're going to write it with a k plus 1. This one is a little different than the ones that had sums because you're not necessarily going to come up with a goal that you're trying to get equal to. All right, we have this inequality. So this takes a little bit more logic and maybe a written explanation than it does mathematical procedures, okay? So, if we look at this, we could rewrite this factorial as k plus 1 times k factorial, right? Okay? We could rewrite 2 to the k plus 1 as 2 times 2 to the k, right? Okay? Now, watch this. We already know k factorial is greater than 2 to the k. We said that here. Okay? So, how will this stay bigger than this?
K plus 1 is greater than 2.
There we go. If k plus 1 is greater than 2, this will stay true. Okay? So if k plus 1 has to be bigger than 2, then k has to be bigger than 1. Alright? But what do we know about all the values of n?
Greater than or equal to 4.
Greater than 4.
They're greater than or equal to 4. So is k bigger than 1?
Yes.
Yes. Okay? Since n is greater than or equal to 4, k has to be greater than or equal to 4. Therefore, it's always going to be true, and we can make our conclusion that n factorial will always be greater than 2 to the n if n is greater than or equal to 4. Okay?
Weren't you supposed to like plug in k plus 1 to like both sides or something?
We did right here. See this?
Oh,
I just expanded that factorial, and I split the exponents up a little bit.
Cause like what I got is 2k factorial is greater than 4k equals to 2k to k plus 1.
Well, you shouldn't have 2k factorial. You're plugging 2k in. It should be k plus 1 factorial.
Aren't you multiplying both sides by 2 or are you multiplying just one side by 2?
We're not multiplying both sides by anything.
Yeah, but where we got 2 times 2k?
Because if you think about this, this is 2 to the k times 2 to the first. You add the exponents, right? You would add the exponents, k plus 1. So really all I just did is I split it up. That's a 2 to the first. Okay? Really, in stuff like this, you don't want to try to do stuff to both sides. You want to keep the sides separate. Alright?
Yeah, leave it for a second.
Sure. Okay, at this point, here's what I want you to do. I want to mention one thing about retake policy and whatnot, but I also then want to mention what we're going to do the rest of the time here. First of all, with retake policy, one thing that has been a little bit of an issue already is seeing people having their cell phones out, or I know with this, some of you are looking at the PDF, so I'm not talking about this moment, but having laptops out, because like I told you, you can't really take notes on a laptop. If you have a tablet or something that you can actually physically write on, that's different. But trying to keep up with the symbols is just not going to work. So, again, I'm not talking about right now, because I know some of you are looking at the PDF that I already had up here, or what you had done earlier. But like when we're covering content, that and having cell phones out, I'm gonna take note if I see that, and if I see that a few times, you're gonna forfeit your opportunity to do a retake, because I'm not going to offer retakes to those who kind of blow off class time. alright? So, just a little warning there, I am gonna take note and keep track. So, keep your cell phones away and try to stay focused in class. For now, what I want you to do is go back to 14. You're gonna get a partner and I want you to compare what you did on number 14 first. And if you match, great. If not, try to figure out maybe if both of you could be right, you just did it a little bit different. Or if one of you has a little issue with yours, you can fix that. After that, we have some more practice, okay? Like I said before, this is just the kind of thing you've got to practice over and over and over again, alright? So here's 17 and 18, 17 through 20, 26 and 27. Okay, so there's just 6 more of these. So work your way through and try, okay? So I'm going to let you guys get started on that with a